Alright, so hello everyone, I'm Srisha Siddharth. I'm a PhD student associated with the Systems and Control Group at IIT Bombay, and I'm also the TA for this course, EE90. So let's begin with the last tutorial session of this course. Alright, so let's look at the topics discussed in this week's lecture. So we are going to first of all talk about determining the steady state error from the given transfer function. And then we are going to talk about uh, state observer design. Just one second. Yeah. All right. So let's start with the first topic. So you must have already seen this before. So let's recall. Okay. So given, for example, the transfer function g of s as the ratio of the output and the input, then the steady state error is, so for example, for a step input, we have ys as g of s r of s, then limit s tending to 0 s time by s, limit s tending to 0 s times g of s times 1 of s. So this is yes. Alright, so let's look at a few questions. Okay, so if we have some error dynamics, then recall that. So let's first look at the block diagram. So this is the block g of s. This is the output y of s. We take a feedback through this block h of s to get the closed loop, and then we have the desired output, right? R of s, which you want to track. For example, the step input. So we have the equivalent signs, and we have this. So this is the error signal E of s. And if we write down the equation from the block diagram, we have Es is Rs over 1 plus Ds Hs. Okay. So for example, for if we have a unit step, so limit s tending to 0, the error becomes s, and we'll substitute 1 by s for the Laplace transform for the unit step times 1 plus Gs Hs. So this is equal to, alright. So let's see. Okay, so let's say that we have a closed loop transfer function. So consider the transfer function. Uh, Closed loop transfer function. It's given by T of S equals to 10S plus 50 over S cube plus 7S square plus 35S plus 50. Okay. So we have this closed loop transfer function means that we have this as a ratio of, let's say, output over input. And we want to track the unit step, that is Rs equals 1 over S. Okay, so then the error, for example, for unity's feedback gain. So let's say that uh, assuming unity feedback system, the error E of S is simply Ys minus Rs. You can write Ys as Ts times Rs minus Rs. So this is the expression for the error. And to talk about the steady state error, so for example, let us denote this by ESS, that is given by limit s tending to 0 S of Es, which is S times Rs Ts minus 1. Okay, so let's apply this to our case. So we have Ts already given, so let's say ESS equals limit s tending to 0 S over 1 by S, and then we have the transfer function minus 1. So this gets cancelled, and let's evaluate the limit then. So this is 50 over 50 minus 1, which is C. So if instead it was a ramp input, for example, 1 over S square, then let's see what the steady state error would be. So in that case, ESS is going to be limit s tending to 0 S over 1 by S square 10s plus 50 S cube plus 7s square plus 35s plus 50 minus 1. Okay. So we cannot calculate this because the limit does not exist. Let's see, 10s plus 50 is 35s plus, okay, so the because the limit does not exist. Alright, so let's look at some more cases before we move on to the next topic. Okay, so we have been given a system. So the block diagram is given. And then we have this feedback and we have RFS. Okay, so we have to determine the error due to step input. So let's see, the closed loop transfer function is, or we can just simply write what E of S is going to be. So let's see. So the closed loop transfer function is given by Gs over 1 plus ds. This implies that we have R is G of S over 1 plus ds. So let's say that we want to track the unit input. So we have the error E of S as ys minus rs, which becomes, so let's say substitute ys here and take rs common. So we have gs over 1 plus gs minus 1. So this is simply 1 over 1 plus gs. Alright, so the steady state error is descending to 0 s times r of s. So we are considering unit input times 1 upon. So substitute the function g of s, let's say 5 s plus 1 s plus 2 s plus 3. This gets cancelled and we have, so s plus 2 s plus 3 over s plus 2 s plus 3 plus 5 times s plus 1. Alright, so let's compute the limit. So we get 0 over 5, right? So this is exactly 0. Let's just check this. Alright, so I hope this was clear. Now let's move on to the next topic. Just a second. See, next topic is state observer design, and in particular full state observer. So full order state observer. Okay, so let's first recall what it is. So let's define the states of the system. X dot equals Ax plus Bu along with some output Cx. Okay, so let's say that we have an estimator which estimates a model. So I'll write this down. So how do we construct estimators is to construct a model of the plant dynamics. So we're going to denote the estimated states by x hat, and the dynamics are x hat dot equals a x hat plus some dut. Okay, so a and b are known because we already know what the model is. Okay, and we also know the initial condition of the original system that we're talking about, and we're considering the initial state of the estimator to be equal to that. All right. So if we have this dynamics, so we have a scheme known as the state observer, in which we include some extra terms in the estimator dynamics. So we have Ax hat plus Bu. So let's write down the time arguments as well. So y is computed from the original states and y hat from the estimated states. All right. And let's say that the error vector is, let's denote this by x tilde or e. So at any given time, this is x minus x hat. Okay, so we want the estimated states to be close to the original dynamics. So we need to see that as limit t tends to infinity, this tend to 0. Okay, so to talk about this, let's first see the dynamics or the error dynamics. So this is okay. So we can just substitute the dynamics of both the variables, and I'll write the final form. This is a minus m times c x tilde. Okay, so if we want the error to go to 0 or x tilde to go to 0, we should have the poles of a minus mc on the left half plane, right? So to talk about the eigenvalues, we consider the characteristic equation a minus mc equals 0, and we are searching for, so we are actually designing such that a minus mc has negative eigenvalues. so that this error dynamics system is stable, and we get that the error converges to zero as time tends to infinity. Alright, so let's say that the objective, so we already know A and C from the system dynamics. The objective is to design M such that this characteristic equation uh, matches the desired characteristic equation. And as we have already seen in the pole placement control design, to get the desired characteristic equation, let's say that we have desired eigenvalues at some lambdas. So we have lambda 1, lambda 2 up to lambda n. So the desired characteristic equation becomes simply the equation formed by these eigenvalues. And then we compare 1 and 2 to find out what m should be. So let's see, we have x tilde dot equals a minus mc x tilde. We have n states. So m is not a scalar, so we have a as n by n minus some dimension of m times c. So for the complete state observer, we have all the states. So y is n by 1. We have this as n by 1. So c becomes n by n. Let's wait a second. Let me just check the dimension of this gain n. So it should be n by 1, right? Uh, yeah. So c is actually 1 by n. Sorry about that. So let's correct this 1 by n. Therefore, this is going to be an n by 1. So the gain vector m belongs to the vector space n by 1. Alright. So we have to design M such that the characteristic equation matches the desired characteristic equation. Alternatively, you can also use the Ackermann's formula to place the poles of A minus NC. So we'll also discuss that now. So we'll do this using the principle of duality. Okay. So there is a remark that there is a connection uh, between estimation and control problems. Okay, so for pole placement, you need the matrix. You have to compute this, right? You have to compute the gain vector k such that A minus bk has desired eigenvalues. So we need A, we need B, and we need k. For estimation purposes, as we have seen, we need A, we need C, and we need the gain vector M. Okay. So from the principle of duality, we have that we should take these as transposes. So let's see. So this is the Ackermann's formula. So we have to design the gains for A transpose minus C transpose M transpose. Alright, so this is the characteristic equation which we need to match with the desired characteristic equation. Alright, so this is clear. Let's look at some questions. Okay, so this is the second question. Yeah, alright. So we have observer design by matching coefficients. Okay, let's see. So we have been given the transfer function. G of S is, let's see, 407 S plus 0.916 over S plus 1.27 and S plus 2.69. Okay, so the problem is to design an observer with a transient response described by. So we have a second order system. So the response is described by the damping coefficient zeta 0.7 and omega n equals 100. Okay. So one of the main things to note about observer design. So before beginning observer design, always check whether the system or whether the pair AC is observable. So only then you can go ahead and compute the gain vector n. Okay, so let's say for the plant, for the given transfer function, we have these matrices A and C. So I'm going to write this down directly. 0, 1 minus 3.42 minus 3.96. And C is 372.81, 407. Alright. So this is a second order system. We can always check the observability. This is CCA. So let's see. This becomes so C times A is 0, 1 minus 3.42 minus 3.96. So this is 407 times, and then we have 372.81 minus 407.96. Okay, so the observability matrix become 372.81, 407, So you can check that the determinant is non-zero. So we conclude that the pair AC is observable. Now we can go ahead with the observer design. Okay, so let's see. We want to design again such that we have the desired eigenvalues of this matrix A minus MC. Or in literature, you will also find the gain matrix denoted by L. So A minus LC. And let's see that. So what's the dimension of the gain? It was n by 1, right? So we have L equals L1, L2. So we have A minus LC as 0, 1 minus 3.42 minus 3.96 minus L1, L2. 372.81, 407. So let's compute this. First one is simple, minus 372.8, 1 times L1, then 1 minus 407 L1, and then we have 3.42 minus 372.81 L2, and then we have 3.96 plus 407 L2. Okay. So then the next step is to calculate the characteristic equation of this matrix. Okay, so I'm just going to write this down directly. You can check it. Lambda square is 3.96. This is straightforward. 3.42 minus, okay, just a second. Okay, so this is plus. Let me check. Yeah, 3.42 plus 372.81 L2 plus 84.39 L1 equal to 0. This is the characteristic equation. And from the problem statement, so the objective is that we want this to be 0.7 and omega n to be 100. So then what's the desired characteristic equation? We have lambda square plus 2 into 0.7 times 100 lambda plus 100 square equals 0. So we have 140 lambda plus 10 to the power 4 equals 0. So this is the desired characteristic equation. And now we just have to match the similar parts from this equation and this one to get the value of L1 and L2. Okay. So one comparing the coefficients, we get that L1 is minus 38.397 and similarly L2 is 35.506. Okay, so after this whole design, you can always check if you have made the right calculations. So you can check that we have L now as minus 38.397 and 35.506. So check that A minus LC, the eigenvalues of this are exactly the eigenvalues of the characteristic equation. So if these are equal, then this computation is correct. Okay, so let me see. Alright, so let's look at another question which uses Ackermann's formula for observer design. So we have question 4. So let's say that we have a system x dot equals ax plus bu with a as 0 and of course y equals cx with a as 0, 1, 0, 0, b as 0, 1 and c as 1, 0. Okay, so design the state observer for the system. Design a state observer for the system. Alright, so let's see. Given that the observer poles are located at s equals minus 10, minus 10. So now we know what the desired characteristic equation should be. That is s plus 10 squared equals 0. So we have s squared plus 20s plus 100. So this is desired characteristic equation. Alright, and now we need to apply the Ackermann's formula. So we have just seen that we need to, okay, so first of all, let's check if the system is observable or not. So observability matrix is C and AC. Sorry, CA. So let's impute CA 1, 0. So this is simply 1, 0 again. Let me check. Yeah, sorry, this is the identity matrix. Determinant is of course 1. So determinant of 4, which is 1, implies that the system is observable and the pair CA is observable. Okay. So for the Ackermann's formula, so from the principle of duality, we are actually talking about the system A transpose C transpose, right? So let's look. Yeah. So we are looking at A transpose C transpose and we want to place the poles of this at the desired locations. So if we have A transpose and C transpose, then from the Ackermann's formula, what is U inverse? This is simply C transpose, A transpose, C transpose inverse. Okay, so we already have the observability matrix as CCA. Then we have observability matrix transpose as C transpose, C transpose, C transpose. So this is C is 1 0, and we have transpose of CA. So we have 0 1. Okay. So the inverse of the identity matrix is again identity. So we have this here. Okay. Then we have to find the desired characteristic equation, but for A transpose. So this is A transpose squared. We're talking about the second order system as alpha 1 A transpose plus alpha 2. So we know what A is. So let's substitute. Uh, and we also know what A alpha 1 and alpha 2 are, right? From the desired characteristic equation. So this is 20 and this is 100. Okay, so let's compute what E transpose square is. So identity times identity, right? Oh, sorry, A is not identity. It is 0 1 0 0. Okay, so let's just compute A transpose first. Transpose of 0 1 0 0. And then A transpose squared becomes. So it's 1 times 0 and 0 times 1 and then 0 again. So this term drops out. Then we have 20 times A transpose, that becomes 0 0 1 0. This is constant times identity matrix. So 100 times 1 0 0 1. So this is simply 100 0, so 20 and 100. Okay, so the observer gain matrix are computed using the Ackermann's formula. Is given as, so say M transpose is actually equal to 0 1. Then we have U inverse, which is identity. And then we have the desired characteristic equation. 100, sorry, the the equation from Cayley-Hamilton theorem for A transpose. So 20 and 100. Okay, so this is simply 20 and 100. So this implies that the gain matrix that we're talking about is 20 and 100. So just to recall, when we're talking about estimation and we need to compute the gain using the Ackermann's formula, we're talking about the system A transpose C transpose. So actually we are uh, designing for poles of the system to be at some desired location. So if this is the system, then the gain would be M transpose and it is given by 0 1, and then from the lecture we have this inverse, right? So Q for this is the controllability matrix formed by A transpose and C transpose, which you have just seen is computed using the observability matrix for this case. And then we have phi of A transpose instead of A. So this is just alright. So let's look at some more questions on state observer design. Just 1 second. Yeah. So we have a question. We've been given the state space model. So we have the system x dot equals 0, 1, 20.6 and 0. This is A matrix plus B times 0, 1. And then we have the output as the first state. So the objective is to design a full order, or sometimes known as complete state observer, to estimate the state vector. The observer matrix, uh, the observer matrix is required to have eigenvalues at, so there are double eigenvalues at -8. Alright, so then we have the desired characteristic version. So we have s plus h squared, s squared plus 16s plus 64 equals 0. Alright. Then we have, so we have A transpose equals 0, 1, 20.6 and 0. And phi of A transpose is A transpose squared plus alpha 1 times A transpose plus alpha 2 times identity matrix of size 2. Okay, so we already know what these are. This is 16, this is 64. Push it out. Let's compute A transpose squared. We have 20.6, and then we have 0. So again 0 and then 20.6. Let me just check this. Yeah. Okay, so let's substitute this in phi of A transpose. We have 20.600 and 20.6 plus 16 times 0, 20.610 plus 64 times identity matrix. So let's see, this becomes 20.6 plus 64. Yeah. Then the second element is simply 16 times 20.6. Then we have 2 zeros, just 16. And then finally 20.6 plus 64 again. Okay, so this is phi A transpose. You can simplify this further. Now the next matrix that we need to compute is, so for the state observer design, we of course have to check the observability matrix C and CA. So this is given by, so let's compute CA first. C is 1 0, 0 1, 20.6 and 0. And we have, this is 0 and this is 1. Alright, so we have 1 0 0 1, which is identity again. So according to the formula, we needed to compute U inverse, right? So let's see, U inverse is C transpose, U transpose, C transpose inverse. And this is actually, so U transpose inverse. This is simply identity. Okay, so let's plug this in the Ackermann's formula. M transpose is going to be 0 1, then the identity matrix, and then phi of A transpose. So we have 84.6 here, then we have 16, and then we have 16 times 20.6. Okay, so this is simply 16 and 84.6, or the gain factor n is actually 84, 16 and 84.6. Okay, so now let's see the question. This was question 4. Sorry, 5.